So, yes, I'm going to talk about conditional entropies. So this is a joint work with Milan Godarti and Marco Tomamichel, who's also in the audience. Okay, so a motivation for this. So we have seen throughout this conference many relative entropies, such as PET, sandwich, with several applications. And actually, if you look at conditional entropies, well, there is even more. And actually, once you're given a relative entropy, there is always a way to define a conditional entropy, and this brings into the picture even more quantities. So, motivated by this, there is this question, is there a unique quantity? And actually, in the classical settings, for example, when we look at entropies, under some operation actions, for example, monotonicity under unital channel, which means adding noise to the system, and additivity under tensor product, we can identify what is a general form of a Renner entropy, and of a general entropy. And this would be given by the so-called Renner entropy, which is just sum of the alpha power of components of a probability vector. And motivated by this, we could ask, what about the quantum case? And well, maybe that's not the case. Maybe we cannot single out a unique quantity, but actually we are also interested in the question, well, we have many quantities appearing in the literature and with operational interpretation, and the question could be, at least, can we unify those one under a unique mathematical framework? And another question is, okay, why do we care about this? Well, once we know the structure behind these quantities, we could think of what singles out certain entropies rather than others, so which kind of parameter ranges at some properties for certain kind of problems. And also, I believe we could understand it better, all these kind of scatter results in the literature, and usually a better understanding of existing results could lead to derive new results. And actually, in this talk, I will show you that for conditional entropies, we actually do find an underlying mathematical structure behind the most studied conditional entropies. Okay, so most of you know the von Neumann conditional entropy, which is just the minus the omega k relative entropy between a Bapper-Stahl state rho B and an identity A tensor rho B. And you can also write this one as an optimization problem by just optimizing on the second argument over all states sigma B. And it turns out that you can play this game with other relative entropies, and these are, for example, the PET and the sandwich relative entropies that, for example, have operational interpretation in hypothesis testing. And actually, there is a family that unifies these quantities, and this is called alpha Z Renner divergences. And I believe you've also seen this one a few days ago. And well, then we can build a conditional entropy by just playing the same game, and we can define two versions of this. So one is called arrow up, and is the one that we minimize over the second argument, and the one is arrow down, where we just take the margin on the second argument. And so for the omega k relative entropy, when this quantity is omega k relative entropy, these two versions coincide. But this is not usually the case of when we consider Renner relative entropies. So this leads to two different definitions. And well, using all this relative entropy zoo, we can build all these quantities, so pets up, pets down, sandwich up, and sandwich down. And the question is there an underlying mathematical structure behind all these notions of conditional entropy? So actually our starting point is also from this duality problem. So the von Neumann conditional entropy satisfies this property, so the entropy of A given B plus entropy of A given C is equal to 0 for a Q state, tripartite pure state. And we actually also have duality relations for these kind of generalizations, Renner generalization of them that relate, for example, sandwich up, or pets down, or sandwich down and pets up. And all of these have a kind of relations between the parameters, but from here it just looks so really not clear whether there is a unifying structure, and actually also they all have different proofs. And so it's not so clear how one can actually unify these relations. And another question I have is, well, we've seen that this alpha z Renner relative entropy unifies both the notions of sandwich and fed. And we could think of what is the dual, in this sense, of alpha z Renner relative entropy, for example, conditional entropy, for example, arrow up. And okay, this leads to our new family. And this is the new conditional entropy, which looks quite long. But the main idea is basically to consider kind of an alpha z relative entropy, and then in the second argument, use a mean between the marginal rho b and sigma b. And then we optimize over all states sigma b, and depending whether the function is, this means that depending whether the function is concave or concave, we take the max or the mean. So the concept is here. We take this kind of weighted mean, lambda weighted mean between rho b and sigma b. So the case lambda equal to 0 recovers the arrow down. So you can see that here rho b disappears, and well, sigma b disappears, and lambda equal to 1 recovers arrow up. Okay, so here is the whole picture. So we have this kind of mother quantity, and then for lambda equal to 0 and lambda equal to 1, we get either arrow down or arrow up. And then from there, we use that for z equal to alpha and 1, we recover pattern sandwich. And well, we also have these kind of limits that are applications in QKD. So for these limits, we have mean and max entropies and various mean and max arrow down, arrow up, various notions that have been used in the literature. Okay, so actually I want to give you a bit of technical details in this talk. So what actually led us to define this quantity? And well, the original definition to me, at least, it doesn't look very symmetric. And actually how we found that definition is through the purification kind of picture. So actually, if you look how duality relations, for example, sandwich are proved, you would have to replace, for example, the outer power before the trace with an optimization over some quantum states. And then your state rho AB, you would use some trick to transform it into rho C. So you would have the kind of the sandwich term on our right-hand side. At least for let's say for alphas. So actually, to have a symmetric form, then we would, that is inspired by duality, we would have to have also on the left-hand side the same mean between rho b and sigma b. And this is how we came up with this form that, with this particular kind of mean that is not a geometric mean, for example, that kind of unify the picture. And actually this, we took some time also to find the relations between this alpha hat, zeta hat, and lambda hat, to lambda, z, and alpha. And actually, from here you can prove immediately duality relations. So from that form, it's actually apparent that the duality relation must be this one with this choice of parameters. And actually, this form that I gave you before, it's actually very useful not only for duality relations, but also for chain rules. I will talk about it later. So, but actually, what is a conditional entropy? Well, I haven't told you what might be the axioms of a quantum conditional entropy, and what we look at here is at least we identify these properties. So one is monotonicity under unital maps on the system A, and this means adding noise to the system A should increase the entropy. Then the other one is monotonicity under any map on the P system, and this tells you that basically you can manipulate at will your side information to get information on your primary system A. And the other one would be additivity for independent systems. So basically, since the two states are not correlated, we expect the conditional uncertainty to some. But actually, even more properties can be demanded, and we refer to this paper for other kind of stronger axioms. But at least here we mostly look at this one, but I will mention the other ones later. Okay, so one question is, okay, what about, is there okay, I've given you these definitions, but is there a way to recover our definition from an underlying divergence that might not be the bet or the sandwich or the alpha z, but any? And actually, we show that our conditional entropies cannot be recovered in this form. So for any relative entropy d, so I mean a quantity satisfied data processing and additivity, we cannot write our conditional entropy in this way, either minimizing or replacing the second argument by the marginal. And this shows that actually the set of conditional entropy is larger than the set of divergences or relative entropies. And so this shows that there is a way from a relative entropy or a divergence in this case to construct conditional entropy, but there might be in this way, but there might not be conditional entropy that can be recovered in this way. And the other point is that, okay, so we have 5 non-commuting terms, and does this trace function actually satisfy data processing inequality? Meaning that I can act on each all of the terms, and then this trace function will decrease. So this we have with trace functions before, where we have a 1 term left, so not 5 but 3. But in this case, when we have 5 terms, then this doesn't usually happen, and this actually makes the proof of the data processing inequality quite complicated. So okay, our first main result is to characterize the data processing region. So okay, the parameter range is not so important, but under, for example, the tensor product of a unital channel and any channel on the conditioning system, then the conditional entropy increases. And actually, here we can see that this lambda that was originally made to kind of interpolate between 0 and 1 can actually be negative, and it can actually go to minus infinity. And at minus infinity can recover even a conditional entropy that is not the standard von Neumann conditional entropy. But that's a caveat. And actually, we could show also some monotonicity under more general channels, and for example, on condition operations. So you do a measurement on the B system, and then depending on the outcome of the measurements, you do a different unital map on the A system. But I haven't put it here. Okay, I want to give you a bit more details. So what's the point? So we use a convexity property of a certain trace function. So, and this might have also applications maybe outside in entropic quantities that involve a large number of commuting terms. And the idea is that this is what we want to prove, a convexity of such a function in A and B. And the point is that the order matters. So here you can see that A is on the left-hand side, and B is kind of in the middle between B and C. But if you just look at the literature, what we have is generally nice properties for this other function, where A is outside and B is on the inside. And K is actually a constant. So the problem is that B is actually, in our case, is in the middle, is between A and C, and not in the middle of the trace function. But actually, this optimization plays a role. Indeed, you can write what the previous one, the last one I gave you, as an optimization problem by introducing an optimization over C. And actually, this shows that if we set K equal to the identity, then we actually have B in the middle. And actually, this shows that all the proofs, this proof strategy that worked for this function, where we had this kind of closed form solved, actually work for our case. Our case is slightly more complicated because we have a bipartite structure, so we don't have a closed form for this C. But still, we can actually play the same techniques and get the results we want. Okay, another form that is nice is, okay, I told you we cannot write as a minimize or just replacing the marginal of relative entropy, our new conditional entropy, but we can actually do it with an asymptotic formulation. So we can write as a limit n to infinity of alpha z Renner divergence of rho A B tensor n with the identity A tensor geometric mean between our state rho B and what is called a universal state. And okay, maybe I don't have to specify much about the universal state, but it's a state with very nice properties. So for example, it commutes with any permutation invariant states. And this is the Kubo geometric mean and satisfies this nice property that under the action of channels, the channel on the mean is smaller than the channel acting on each element of the mean. Okay, I want to give a very simple proof of DPI. Okay, through this, at least for lambda equal to 0, where the geometric mean satisfies that nice property, there is a very simple proof of DPI. So if you remember, this is our form of alpha z conditional entropy. So we want to start with this. For any n, we find an inequality, and then we take just on both sides the limit n to infinity. Okay, so for any n, we need to find this inequality, and the first step would be to use the DPI of the alpha z. So then we have with the channel on B, on rho B, and this geometric mean. Then we use the property of the geometric mean, and the fact that the d alpha z has a minus sign, so it's actually anti-monotone on the second argument. So then we can split the channel on rho B and the universal state, and then we can use that any permutation invariant state can be again upper bounded with the universal state up to polynomial factors. So then we get rid of this channel on the universal state, but we get log n factors, but those don't matter because when we take the limit n to infinity, these disappear, and we actually get on both sides what we would want. And actually this simple proof extends also for a more general class called conditional mixing channels. Here is the reference that are defined to be under kind of some more general requirement. Okay, maybe I want to see. Okay, so then we want to show stronger kind of property for this function. So one thing is about the monotonicities in the parameters. And here we are dealing with a lot of non-commuting terms. So the monotonicity in Z, for example, is proved through Arachilid theorem inequalities. So for example, for t is more than 1, basically you can just take out this t exponent on A, B, and A outside and get an inequality. But this doesn't usually hold for more matrices. But actually, we show that in our case, once you optimize one of the matrices, then this actually holds. It doesn't. Okay. And the point is that the matrix C does not commute with others. And so somehow we don't even have a closed form of that. So somehow we need to use some techniques, and the point is that we use an asymptotic formulation where this C kind of can be replaced by a universal state and can make it commute with the others. Okay. Applications. Okay. Here we don't have applications, but we have applications in mathematical sense. So that's why the two kind of. And okay, so once we have a common framework for these quantities, similarly to what we do with resource theory, we might ask, can we hunt the archive, basically, and find a proof for sandwich, and generalize it for example, for pets. And this is actually what we did. So there was a known chain rule for sandwich conditional entropies, and so there is this relation between the systems A, B given C is bigger than A, B, C plus B, B, C, B, and C, and the parameters satisfy this relation. And the fact that now we understand that there is an underlying mathematical structure. The idea is that, so for pets, for example, it was not known whether there exists a similar structure, but now we know that all these entropies are the same entropies, so basically we use the same proof to prove a very general chain rule. And this is the chain rule we prove. So we have this kind of complicated relations between the parameters, and this is a very general chain rule for these alpha, z, lambda quantities, but maybe I specified for what we actually need. And for example, in the first case, we prove a chain rule for the pets up and down. And actually the relations between these two the parameters has to be this one, instead of alpha over 1 minus alpha is as 1 over 1 minus alpha. And actually we also find mixed chain rules for pets up, down, with and that mixes with sandwich up and down, and the same one on the third term. And so this is kind of we don't have to write 3 more papers on each of these chain rules. And yes. And with this, I thank you for your.
So, Hao-Cheng, you have a question?
Thanks for the nice talk, Roberto. So in the past few years, there have been many results for characterizing the exact error exponents or strong converse exponent of many different tasks in terms of many different running conditional entropy or information. Some tasks with the up arrow one, some tasks with the down arrow one, even some tasks with a double optimized one. Do you have a reason why some quantities show up in some tasks, some down arrows show up in others?
No. So I don't know anything about applications. But we hope that there should be a reason. And one starting point could be to find a kind of unique way to describe these quantities. But I don't have any insight. I actually haven't thought about this.
Thank you.
So there might be a thing.
Actually, Fred, come to Fred next.
Yeah, thanks a lot for the very nice talk. So just to go back to the idea that you couldn't recover it from a apparent quantity, like from a divergence,
yeah.
It just strikes me that this is not what you would expect anyway, right? Because the first line would be like these would be two extremes of lambda, right? Like you'd have like lambda equals 0 and lambda equals 1, right? Yeah. So I guess what you would expect is something a bit like you had later with a divergence to like a
this one.
Yeah, exactly. So is it possible to get it like getting rid of the limit and having like a minimization, but only on like omega or something like this here? Like, is this excluded or?
So yes. So the point is that the geometric this mean between rho b and omega is not a state. So yes, if you get rid of the limit and write as an optimization, then you would just recover the definition we had.
Oh, okay. So
you would just recover this definition. But
okay.
but yes, but it's not the canonical way people use to derive conditional entropy from Renner. That's the point.
Right, but I guess in this context, I would argue it's more natural, right? So okay. It's kind of
yeah. The right way. Yes.
So I had a question. So there's a closed form for the pets up arrow. Is there a way you can use this
we have closed form for alpha 1 lambda, which is the pets lambda.
So can you get it for the sandwiched up arrow as well? Can you get a closed form for that?
No, for the sandwich is generally not known to. Probably there is no closed form. I believe there is no closed form.
There is no closed form at all. Okay. Thank you.
Thank you for the very interesting talk. Could you go back to the concavity convexity thing where you're considering this with the 3 systems? So just for me to understand this correctly, I think either of those, no? Here in the second line, so you're saying this is concave or convex in B. If you optimize over C.
AB. Jointly concave.
Yeah, but the A is clear, no? But the B is the thing that is not true if you don't optimize over C. But if you optimize over C, then this becomes fine.
Yeah, that's the point of the work. If we optimize over C, then it's fine.
I see. Can you say something about this? I think this is not very obvious, no? Because if you don't optimize, it's really, I mean, there's easy counterexamples.
It's not easy. So you have to use kind of Frank and Leave theory on variational forms, and then you have to do a bunch of tricks with the partial tricks and maximally entangled state. But yeah, it's not trivial to explain it now. But you can look at it.
You want to say something?
Yeah. No, but so okay. So if you go to this, your asymptotic proof, right? Your asymptotic expression. Yeah. Sorry. If you go to the asymptotic expression, you presented that one. So let's say I want to construct a divergence now, and I do the same thing, but now with rho tensor n on the first argument, and then sigma tensor n, and then geometric mean to omega. Can you compute the limit? Does it give you a new divergence like alpha z lambda?
So geometric. So you don't consider you still consider the asymptotic limit?
Yeah, still look at the asymptotic limit. Yes.
On the first argument is rho b tensor n.
Yeah, rho tensor n, because it's not a bipartite system now. I want to do a relative entropy, so rho tensor n, and then the second one, sigma tensor n, the geometric mean lambda to omega. Then I take the limit, and then your proof of data processing should go through.
Yes. So the point is that if you don't have a bipartite structure, or
I mean, if you go to the proof, I think it might go through.
Just make sure that there is no closed form for this.
It might be, I don't know. But it looks a bit like what.
There might be a closed form, but geometric mean. Okay, geometric mean.
It might be related to one of these barycentric divergences that Milan started.
Yes. The different thing is that there is no asymptotic.
Yeah, sure, no, exactly.
Yeah,
no, of course, I don't know. Yeah, it might go away or not.
Maybe there is. Maybe there is.
Yeah, so I'm not really sure I should thank you for your talk. I'm a bit worried that we have more and more parameters, so where will it end?
Okay. Where is this going to? An infinite number of parameters, I guess. And but we have some words coming to try. But we are not scared of infinities, right? Like even real numbers are infinite. So and we work every day.
But are we going to need names for all of these, or?
That has to be sorted out.
Yeah, more of a comment than a question. I would like to point out that yesterday was Roberto's birthday. I wanted to wish him a happy birthday.
I'm sure we should take any more questions. Yeah, either that or we. Okay, well let's thank all the speakers, Roberto and all the speakers for this session. So